And then I'm going to share this screen. Okay, why they don't have that screen? Share. Do you see something? Do you see? Do you guys see?
Yes, I
Yeah,
can
no?
see your
Okay, good.
writing, your notes.
Okay, good. Okay. So let's go through this example related to that single group repeated measures. Can you remember we were talking about different types of uh, repeated measures, how to design this one, depend on that given scenario. This one completely randomized design. Then we came to the block design. Block design has been done to the certain extreme through these repeated measures. In that one, we talk about this example. So actually, this is the same example. I'm on this one. Then the response reaction time, and they were doing like a study on that effect of the 4 drugs on the reaction time to the series of tests. Actually, this one, they are looking for the reaction time of 4 drugs on no, actually, they are looking for the effect of the drugs on that reaction time to series of tests. Okay. So this one, if that's the case, this is kind of this is repeated measures analysis of variance. Actually, at the end of the day, we're gonna compare, we're gonna hypothesize the average of this one, average of this one, and average of this one, and average of these readings are the same for in the population setting. And then versus its counterpart, at least 2 of them not going to be the same. We don't know which 2. At least 2 of them not going to be the same. Either these 2 or these 2 or these 2. How many the multiple comparison we can build up? We talk about that one. 4 choose 2, which is 6 combinations. So out of 6 combination, which ones not going to be the same? We don't know until we're going to do the multiple comparison. For that one, we do over here contrast. We don't do anything by hand. Okay, that's the same example that kind of like we built in up over here. See, we have just the individual. This is the 4 drugs, and then we're gonna look at this one. They are trying to analyze this one in 3 different ways. One, that using the completely randomized design, CRD one. Second one, repeated measures design, RMD design, design, but univariate, taking it as like a univariate. The third one in a multivariate format. Okay, so we don't have to worry about anything. We're not going to do anything by hand, but I want you to see that what's going on behind and get a clear idea. See, this is a study of the effect of 4 drugs on reaction time. See, 2 series of tasks. So this is the reaction time for these other drugs. So we have like a one group, group of subjects. Okay, and then these are the readings. So now it seems like we have a contingency table. We have a contingency table like they see 1, 2, 3, 4, 5 rows and 1, 2, 3, 4 columns, and then in that way we have a row means and column means and column standard deviation. You can get all these and then get grand mean. And I put the I goes from 1, 2, 3, 4. G, I'm gonna call that one G. In textbook they call it is referred to as K. I'm not gonna put K because I really need that K to use for some certain index down the road, because I, J, K, those are indices. G, I'm gonna say that a group. Okay, it's easy. But in textbook they are using K. By any chance, G stand for how many groups? First one, second one, third one, fourth one, but all these being blocked, see, by subject, blocked by subject. That same person has to go through all these drugs, and then they're gonna record their reaction times. Okay, once they've been entrusted with certain task. Okay, so we will analyze this set of data in 3 different ways as a completely randomized design, CRD. See, as a CRD. CRD. We can remember CRD. See, in the very beginning, I talk about CRD in the golf ball example. See, that's the same thing. Okay, see, this setting. Who can get this one in this setting? Doesn't matter. It's not necessary to be go to the block design. You can get this done in this one and see whether we're going to come up with the same results. That's what we are trying to do over here. Second one, univariate repeated measure. Third one, multivariate repeated measures. So 3 settings. So this is kind of like a same exam. That's why we can sometimes when we run that SAS code, we're going to say no uni. No uni means I don't need the univariate repeated measure analysis. That's why we put the no uni. See? So that one being taken out. Okay, let's go to the completely randomized analysis of the drug data. This for this one. How do you get this done? This you have already done this kind of stuff in previous class. You're gonna hypothesize on in their population. Okay, these are population averages. Reaction time averages, not the y bars. Mu1, mu2, mu3, mu4, all gonna be the same. It's being tested against its counterpart. At least two of them not going to be the same. See, I and J at this moment, if you put 1, you cannot put 1. That's what we meant over here. But for I and J, you can assign 1, 2, 3, all the way up to 4. I'm sorry, the 4 as well here. Okay, should be 4. 1, 2, 3, 4. All the numbers in that sense, the I and J is same. But in here, if you put 1, you're not going to compare and contrast 1 with 1. There's no point. 1 and 2, 1 and 3, 1 and 4. If you put 2, 2 and 1. If you can put the same number, or you can write in the plain English and say at least 2 of the averages or population means not going to be the same. So the sum of squares between, we're going to say SSB. Or some people, they used to put B here. Or sum of squared within. Some people use the W here. And the sum of squared total. There are 3 types of sum of squares. Okay. So this one, sometimes people refer to as the treatment sum of squares or sum of squared treatment. Doesn't matter. SST, sometimes we call that one SST, between groups. See, if you go to this picture, this group and this group. Within means inside. Inside you can check the variability. And at the same time, you can check the variability between 2 groups at a time. 2 groups at a time. See? That's what we call the between. Within means inside. Inside we have a variability in our readings, as well as there are variability between these groups as well. Those everything should be taken into account. That's what we are trying to do over here. Okay. So your formula should be summation of I goes from, my I gonna go from 1 to 4. And J gonna go from Ni actually. Ni means if you put the N1, they're not gonna be the same. In most cases, the cell, this is called the cell size, not gonna be the same. Some readings might have been deleted. Let's say you are collecting data, some people, they don't gonna participate sometimes. See, 4 and 5 for this one. Then again, they come and participate here or something like that. In that sense, you might gonna miss in here. But in this case, fortunately, we have equal sizes, see? Equal frequencies for all groups. Okay, that's why I put Ni equals to N equals to 5, sorry, 5 people. So you go to the mean, see, mean data, mean of this guy, mean. Okay. So the mean of this one from the mean of that one, you have to subtract the mean of grand mean. Mean of that group, subtract the mean of that one. Okay. In this setting, see, let's say that you have a mean here, see, 26.4 minus 24.9. See, the difference. That's between. See, it's with respect to the grand mean. You have seen this one in the very beginning, and 600, 605, I did this one in large scale. Can you remember? I draw that one all the time to with respect to the grand mean, and then when we have like a categorical data, the numerical data, all the time we did that one. See, mean to mean, and since there's no this one, see, J, there's no J, because of that it should be N. Okay, so simply that means this is how you're gonna do. See, 5, go to the grand mean of each group minus the grand mean square. Mean of this one like that. See? That's how you get this one. See, that's the sum of squared between treatment. Sometimes we call the treatment, see, SS treatment, SSD, SS treatment, that's the same thing. And then within has another name, within sum of squared or error sum of squares. Error sum of squares and within, in this case, they both the same, but in blocking, they're not the same. That's what I want to emphasize over here. Within means error sum of squares. So sum of squared error. You can read SSE, sum of squared error, or error sum of squares, from left to right, right to left. You go inside the reading, from that particular reading, you're gonna just subtract this guy. You have seen this one actually. This kind of stuff you have already seen. This is like a see, if you go to this setting, see, if I draw this one for you to see in a new the graphical fashion, see, you have seen here, see, this is your y. Y means your response. Response variable y is nothing but reaction time. See? Then you have here what? You have a drug type. Type 1, type 2, type 3, type 4. Say you have a grand mean somewhere. See, y bar. Grand mean somewhere. You can remember. Grand mean is how much? Grand mean is 24.9. And each one, see, it has its mean too. I'm gonna draw and then come back to this one. Okay. See, 26.4. Some are above the grand mean, some are below the grand mean, doesn't matter. 26.4. 25, see, y bar 2, 25.6, 15.6. And 32. Right, that's it. Y bar 1, y bar 2, y bar 3, y bar 4 for each group. If you really want to find, see, if you really want to find the between, that means you are taking this one minus this one, see. This is for between. See? Mean to mean, mean to mean, see, mean to mean, see, this to that, this to that, this to that, then square. Because we wanna make sure that once you add those, they're gonna add to 0. To prevent that one, we're gonna square. We had that broader discussion in the previous classes. That's why we squared them. Okay, the distances are squared. That's for the between. For within one, that means between means treatment sum of square. Within means you go inside and you subtract. Let's say that this is your point here. From this point, you're gonna subtract this guy. See? That they are on me from all the points. Those are called in between. See?
Professor, so, where are you writing? I can't see where you're writing.
No, you cannot see?
Oh, no, I only see the PDF.
Oh, okay. But I dragged that one to, can you see this one now? I'm sorry. Okay, I'm going to go back again. Can you see now?
Not what you're writing, just the
not
PDF.
Not the still the PDF. Okay. Okay.
I see your handwriting, but yeah.
Okay. Okay. What happened? Okay. I'm gonna share again. Okay. That way. Okay. Good. Now it's in. Now you can see. Can you see now?
Yes.
Yeah, now you can see. Yeah. See, this is the. Did you see earlier the picture, even this graph? Okay. See, y response variable with the reaction time. These are the drugs type. Okay. 1, 2, 3, 4 on the x-axis is the grand mean. This is that they are each and every group's mean. Those are called the group mean. See, y bar 1, y bar 2, y bar 3, and y bar 4. If you take the difference between that group mean and the grand mean, that's and then square and then sum them up. We're going to call that one the sum of square between. And then if you take the reading between that, any reading within that one and their own mean, that's going to be within. Okay, this is for within. This is within sum of square. This for between sum of squares. Okay, so that's the same thing that we have built up over here in this PDF. Okay, that's the same thing. So see, so we go to here. We have reading. I'm gonna subtract their own mean. See, go to reading. I'm gonna subtract this mean. See, this minus this guy square plus this minus this guy square plus 24 minus this one square and then plus 38 minus this one square, this one plus, done. Then you go to this one, 28 minus 25 square, like that. They keep going until you are done with all the 24 times 5, 20 entries. See? That's for the within. It's called sum of squared error. Within sum of squares, sum of squared within, error sum of squared, sum of squared error, any name you can call. See, this one eventually get this one. In question number 1, we are expecting you to do this one by hand. When you want to do this by hand, that you can build up. If you want, you can use the Excel. Oh, but you can give a try on that. SAS put a loop. Okay, I'm working on that one. I didn't put that one loop yet. But I just for the related to homework. Okay, it has the same kind of a yeah. See, okay, this is by this one. Then I need the row means. I need the column. The row means you can take this one in both ways. Okay, in this case, and then to get the grand mean, I use that one. Okay, so that means that for the simply this. So see, this is related to homework. Okay, in the homework we are trying to build up this one. See, this one. This is the one we are trying to build up. Analysis of variance table, ANOVA table. It will contain. See, drug is the treatment. This is the error. Error. This is so. Sometimes we call this one, as I said earlier, between sum of squares. This one within sum of squares. They are degrees of freedom. They are type 3 sum of squares. We can talk about that one later. We have to, at a certain point, I have discussed that one in large scale in 620, I think. We were supposed to talk about that one in regression, type 1, type 2, type 3, one. And mean square. F value, probability, see, GH, and then adjusted probability. And then based on this one, this is enough for us to make the conclusion at the end of the day. This is for the multivariate. This is for the multivariate case. This is for the univariate case.
And so even though when we run this, we say no uni, it's still giving us this univariate output. In SAS, we specify no univariate or no uni.
Oh, I think that. I'm sorry. That I think I'm looking at the wrong place. This
I'm just- no, no, I'm just asking.
no. This uni. No. This one for the. Sorry. This one should be for the. Okay, we say no uni. No uni means like we don't have the univariate one. Okay, univariate one. Okay, then this one for the CRD. Sorry, that one. This one for the CRD, the completely randomized design result. That's the one that you are looking for. This one. Can you remember this one? I'm still on the CRD here.
Oh, okay.
Yeah. Sorry, that this is CRD. CRD, but that's the univariate setting. I'm gonna show you here. Okay. Okay. This one you don't have. This one. See, come this one. That this is the one that we are working. This is the one that we're gonna get it. But when you put the no uni, you're gonna get rid of this one, univariate repeated measure, which is the block design. You don't have that one on that one. Let's run that one with the no, which I'm gonna take that out and run. Okay. Okay. This one, get rid of this one. Let's say that it's gonna show these 3 of them. See, This is from the GLM procedure. See, GLM procedure, that one. Okay, then what was this one? This is a multivariate case. This is a multivariate. Subject effect. Okay. So 146. No. So in okay, let me see that as a example. Did you have this one? I think you had this one, no?
Yes, I have that.
9.7, no?
I believe so.
I think let me check that one. And 9.7, 146, I can remember there that one. So they here that they call this. I think the way that how this been worded, they call the no uni means for the this CRD one. Look at that. I'm gonna see. We don't see that one. When you put that one, no uni, but no uni should be definitely the univariate one. See. Univariate statistics, okay, but I'm gonna run this one, no uni, okay, but see, you have this table for the way that they were repeated, univariate repeated, this one univariate repeated, this the multivariate repeated. We don't have a CRD one. CRD one is the one they are taking out by telling no uni. See, I'm sorry, that's okay. I think you have I saw that you had a 9.7. Let me see. Can you check on that one, David? You have 9.7 for here for 146.
Yeah, let me look. I have to.
Yeah,
I don't have my normal big screen. I'm on vacation with my family, and I don't have my normal.
Don't worry. I can check on one side. Don't worry. I you send the email. I can check. Okay. Okay. You had.
I think I have 7.49 for my sum of squares.
Yeah. Then, yeah. Yeah. Because I know that what happened was that. So, but they are still something because of the degrees of freedom. That's okay, but it's not. It's drastically different for a reason, because that one, this one for no, not this one. I'm sorry. This one for. No, is that the right one?
The one I'm running though is against a.
Yeah, I'm gonna run this one by itself.
Yeah.
Make sure.
Oh yeah, that should be the right data set.
Excuse me. So this is the 92. Yeah, this one for univariate repeated measures. But the question one you have to run for the CRD, which is this one. So that answer, that's why I'm checking whether still we have that one over there. Okay, sum of squares 146.
Are you talking about part A of question 2?
Part A, yeah, exactly.
Okay.
Part A.
I thought part A was just the univariate, not the random.
Oh, not the random one? Okay. Oh, I'm sorry. Oh, okay. Okay, I'm gonna have a look at it this one more time. They were not looking for the CRD, no? Oh, okay.
I think A is univariate.
Okay. I got the point. Okay. Then we're gonna compare. You're right. Okay, we're gonna compare whatever we had over here. This one is the one that I'm eyeing for there. This is the CRD one. This is the univariate one. This ANOVA table is multivariate. This one for univariate repeated measure. This one multivariate repeated measures. This one is for the CRD. That's the one that we block. That's what we want to make sure that which one we block. When we say no uni means that you are blocking the CRD. CRD, see? Okay, then we have this multivariate, univariate, repeated measures only. So as you said that in question number part A, you don't need the CRD for that particular case. You have to get this one. Okay, that's right. Okay. But David, whatever you put that SAS printout, that's right too. Yeah. Okay. So what I'm trying to say, this no uni will take out CRD, which I'm talking about right now here. See, in this particular example, I didn't come to that single one yet. Okay. In the CRD, we're gonna assign these people. We don't block. This is not the way that how this we see. We can tackle that one, even though they have that the first person has experience with the drug one through all the four. Still we can tackle this one as if this has been done completely randomized design, in which this every entry has been done by a single person, not by the same person, but still okay. Whoever had done, we don't take it into account when we do the calculation. But when you design that one under the CRD, you're supposed to get a certain number of 5 people, and they were only assigned to this one. Those 5 people not gonna be assigned to drug 2, then different 5 people. And so do with these 2. In that way, we have to employ around 20 people to get this done. But in a block design, you don't need the 25 people. In a block design means a repeated measures, you need only 1, 2, 3, 4, 5 people only. Okay. Because we hear that there's a variability among the differences, variability due to the differences among these individual will be blocked by designing this one as a like a block design or BRD, or as a this one as a repeated measures design. But under the repeated measure, we're going to tackle that one too with. But when you have a data, we don't care how that has been done. We try to do that one as if it's coming from CRD. See? That's what we are trying to do over here. So here, that's it. You have a sum of square treatment. That same results you can see when you take out the no uni. No uni means that we are suppressing that CRD, this one. Okay. CRD, completely randomized design. So that's the one we trying to do by hand. Then this we got this result. And then degrees of freedom for between is nothing but the group -1. See? Degrees of freedom for B, G -1. And degrees of freedom of within. Within means you go to the total number of observation, total, okay? Total number of observation means that's a summation of Ni, or summation of this should be G, okay? I'm sorry, this should be NG. Don't worry about this, don't look at this one, okay? I'm gonna little bit cross out that correct this one. Okay, this one should be G. This one should be G. This one should be NG group. This one like that. This one should be G. So the total number is, see, that if you want, you can use the formula. Simply you can say that total number minus how many groups. We have a 20. 20 minus 4, which is 16. Then mean squared between means sum squared divided by sum squared between divided by its own degrees of freedom. Okay. Which is that. And the within. This one has another name. I can tell this. Okay, sorry, here. This one you can give another name. Sum of squared error. You can say sum of squared error so easily. You don't have to use the subscript like that. This one you can say, if you want sum of square treatment, sum of square TR, that's the same thing. Okay. TR. See, if you add these two, that's called sum of square total. Okay. If you add these two, you get the SST, sum of squared total is nothing but sum of squared treatment TR plus sum of squared error. But we don't need the total for this discussion. So this is a mean squared, see, mean squared, sometimes you can call this a mean squared what? Mean squared treatment or mean squared model. So many names we have. Mean squared treatment, mean squared between, mean squared model for that one. This one within mean squared error, MSC. If you want, you can use that one as well. And their ratio will create something called the F with the degrees of freedom with the numerator. N stand for the numerator. Numerator means this one, this degrees of freedom. See, this one. This is the degrees of freedom coming from the, because that's the part that we're going to put to the numerator. Because of that, we use this one as a numerator, degrees of freedom, which 3, and this one has a degrees of freedom for 16. Those are responsible for the F distribution. Because why we have a distribution? If you repeatedly do this one, you know you can build up a distribution. Okay, so like this, see? Like this. So your F value, if not, I'm gonna locate somewhere here 4.7, and if you go ahead and look at that that critical value, table value related to this one, see, F critical value or table value with the 0.01 level, see, that's alpha, level of significance. That's the level of significance, you can remember. Level of significance, no? Significance, okay. The level of significance, that's alpha 0.01 to the right of that one all the time in F distribution. If that's the case, by plugging that one into this one, you can get the inverse of that one. At a certain point, we talk about when we were going through that homework number 1, how to get that one using, if you don't have a table, that book that can you remember at a certain point, I showed that one too. See, oh no, not this one, I'm sorry. Should be PC. Point I showed that. Small critical value to get the critical value. Don't say that one. Then on the missing data, where the Mahabhalan is here under that one. See how to get the critical, sorry. See these two, critical value and p value. If you want to get the critical value, you put the probability. You put the probability. The computer gonna calculate the probability to what? To the left. But I have a probability to the right. That's why I get the 1 minus probability. My probability is 0.01. I put 0.01 here. Let's put the 0.01. And then let's go ahead and see 3 and 16. No? 3 and 16. 3 and 16. Then the first degree of freedom, 3. And the other one is 16. 5.29. Is that the same thing we have? Yeah, 5.29. See, I put this A1, but when you're gonna put to the syntax, you have to make sure you put the 1 minus, because the computer gonna calculate. He needs the area to the left. See, you have to put here area to the left, not the right. But we have area to the right. Okay, we have 0.01. You put 0.99 over here. That's what we say. First degrees of freedom, numerator degrees of freedom, denominator degrees of freedom, and you give this one, it's gonna display on its counterpart. If you thinking that, okay, if you want to double check that one and see whether we're gonna get the same answer, 0.01, let me see 5.29. Okay. If you put over here, p value means 5.29. 5.29. 29, 3 and 16. 3 and 16. Okay. 0.01. See, come back 0.01. Like that anyhow. See, so that one, since that this value, see, this value, see, not going to be in rejection region. This is called the rejection region. RR, this is the where that who will be rejected. Who will be rejected? Your H0, okay? Rejection region for H0. What is your H0? H0, you can remember H0. H0 is what? Mu1 equals mu2 equals mu3 like that. Mu2, mu3. The average reaction times are the same. See, we're gonna see. So the rejection region, this is right before the observed value before that one, since that F0 is less than that critical value, okay? Since this one less than observed value less than this one, we're gonna say we do not reject. We do not reject means your test is not significant. We do not reject. You're gonna assume all the reaction times are the same in this case. This is not significant at this level. If it is 0.5, that sometimes it's going to be rejected, but you cannot arbitrarily change the level. Okay, we had that broader discussion in previous classes. Okay, I don't want to get in there at this stage. Okay, so need to look at that one. So that's the result you're going to see when we run this one. You can remember that here, sorry. Let's say that related to the homework, by homework pretty much the same thing, but with like only, let's say we have 1, 2, 3 instead of 3 columns, we have only, instead of 4 columns, we have 3 here. And if you take this out, you can get the answer. Okay, you can check that one too for that particular example. So let me see for that one. I'm gonna see that measures. Okay, let's see here. No, let's see that we get that one. Okay, here. Okay, here. So do we get that one? Okay. Okay, I'm gonna go ahead and see. I need 232, 496. These are the ones that should be in the that our ANOVA table. I don't have for a reason. You know the reason, because I put the no uni. No. 232, 9.4 is that the same thing? 232. That's same. Then this one 49.6 within. This one same. See, mean square treatment. Mean square treatment, even in the univariate case, see this one different. Okay, let's take out that one. So no uni, okay? No uni. So 3,400 GLM procedure model type 1. What if they have that some kind of big number? Yeah, 692. I don't see that one over there. Where is that number? Mm, 32.9.4. These are contrast. These are for the 232. These are for the 232, 9.4. That's the univariate block. Okay. These are the numbers for the multivariate. Oh, yeah. Sorry. Here. Oh, this is only Y1 only. This is Y2 dependent variable. Oh, this is for individual ones. Y3. Y4. Where's the overall one? CRD overall one. Dependent variable Y1 only here. But that's why we don't have this that result. 692 because they completely now looks like the univariate one only that we can display, not the overall one. CRD settings univariate one, this one, this one, and this one, and this one separately. 698. I'm sorry. This one 698, 793. I don't see that one. Sum square. It's not there. Do I say this one? No. No. See, this one Y2, Y1, Y2. Yeah, Y3, Y4. Then overall one. No, this is for the multivariate one. This is for the univariate repeated, multivariate repeated. That's right. These are the contrast. No, that one is not there. Because we were working on the same example over here, but they, since this is under the repeated measure, they don't pay this that much attention for that one. Look like I think they were not built up that one. Only for see individually only. But here we did that one like a overall. Overall, we have this results. Okay, 698. This one, but this value the same as the value that when you do that one using the block design as well, but not this one, not this one, not this one as well. So you can see if you go to here, see 232, sorry, yeah, 232 and 232, see.
So they have the degree of freedom there is 3 and 12.
3 and 12 for the block design, that for the block design. That for the block, because the block design, I'm going to go through that one, univariate block, univariate RMD, repeated measures. These are multivariate repeated measures. But what I'm trying to look for that the CRD one, they don't give the CRD overall. They give the CRD one at a time. See, Y1, Y2, Y3, Y4, because they might have programmed this one in a such a way that they might be thinking that it's not important because that this is under the repeated measures. So anyhow, see, that's why they get rid of that one. The no uni, mainly no CRDs. We don't need the CRDs, but we already calculated to get a rough idea how it looks like. See, if somebody asks that, see, you can look like. But if you're gonna get into that second part, univariate repeated measures, this one it's gonna display for sure. So the see note that the column means for the drug data, the column means, see, column of means. The column of means that in this one, this column, I'm referring to this one, row mean, okay? The row mean column, this column, okay? See, if you go ahead and look at their means gonna differ, see, for the drug data that the participants' average responses to the 4 drugs. Participants' averages, not the drug averages, participants' averages differ considerably, ranging from 16 to 34. I'm talking about this one. 16 to 34. See, each person has their averages, but after taking that their reaction time for each individual. That one will create some kind of a difference that has to be tackled. See, that's what we are doing in the repeated measures univariate case. See? Then our again our hypothesis, conjectures or propositions going to be this one. we have to quantify how much it's going to be differ. See, that variability to be quantified through so-called sum of squared blocks. Sum of squares for blocks, sum of squares blocks, sum of squared blocks, block sum of squares. Okay, any name you can put that one, where we are blocking on the subject. See, blocking on the subject will create a certain variability. That variable has to be taken into account. Once you take that into account, then the error is not the same as within this time. That's what I want to tell. See, these two are not the same. See, last time error sum of squares, so residual sum of squares, that's another name for that one. So many names. I'm talking about in a CRD setting. You can call this one SSE, SSC, or you can call this one SS residual. See, SS residual, res, or you can call this one SS within. That's the same thing that we see over here for you. That means I'm going to put the W here. That's the same thing. But SSC and SSCW not the same in block design. They differ by this much. See, they differ by this much. This is what I'm looking for. You already have calculated this one. Can you calculate this one? See, the block design. See, you really need this one. Okay, you really looking for this one. You can see, you calculate that one. The block design is something. You go to that mean, this mean, from this mean, that see, your individual's mean, you subtract the grand mean, and then take the difference, how far that people's mean, individuals, the reaction time mean from the grand mean. It's the one that being it's due to that blocking, that variability is due to the blocking. We have to calculate that, quantify that one. How much would that be? See how much it's away from that due to the blocking. See, from the grand mean. So you get this minus that, and then square and keep doing for all averages. See, all averages. There's some. See, I'm blocking. Set the blocking. It has been done for all the groups, all the reading. See, J means that's not this. That's why I say I'm gonna call this one J now. J goes from N to 5. So this one mean to mean. See, at the same time, it has to be done for all the groups. Okay, over the groups. See, over the group as well. See, C4 instead of this guy. See, instead of this guy, you're gonna say I'm gonna looking into this one. Okay, instead of this one, I go to this one and subtract this guy. Instead of this one, I go to this one again and subtract this guy. Instead of this one, I go to its average and subtract this one. Instead of this one, I go to this one. That's why we have how many for the first one? 4 of them. But all together for all the 5 people, we have 25. Okay. Okay. So that's why we put that G, the groups should be taken into account. Okay, and it has been done. See, over the groups and over the individual. See, then you get that one, and you know the within one we calculated earlier. You subtract the block, that would be give you that SSC. You need the SSC, SSC or SSC residual. You don't need that. See that one. Then what is the degrees of freedom for residual? Degrees of freedom of error. See, n minus 1 times G minus 1. N means number of individual, 5 minus 1, number of groups, 12. This one G minus 1. See, this one. Make sure that see, degrees of freedom, and then I get the mean squared error. See, I'm gonna get the mean squared error. I need the mean squared error this time. I need the mean squared blocking. Block, mean squared block. Mean squared block is nothing but sum of squared block divided by. Did we calculate the residual? Yes, residual is already within mean. See, within is not residual in this case. You have to subtract this much. But this is due to the blocking. That part has to be taken out. Then they both the same. Okay. Then we get this one. See 232 and 9.4. We can see clearly on this result. I'm here. Sorry. This one more time. That means CRD. We don't talk about CSE here. 232.3, 232.73, 9.4. 232 for the mean squared, the top one, okay, mean squared block, mean squared error, 9.4. And get their ratio, 24.76. 24.76. If you want, you can go to the probability of this one. See, probability, you can look for the probability as the probability means the p-value, okay. Degrees of freedom, again, I'm going to reiterate over here. In the previous case, the degrees of freedom, if you know that degrees of freedom, you can remember G minus 1. See, this is a B. B stands for between, okay, for treatment. See, 3. Now the degrees of freedom, like this, because of the block design, invariant block design. I got this one. Then this is significant well beyond the point or level and is approximately 5 times as large as the F obtained under the completely randomized design. Look at, when we come to this design, it's been rejected. That's why I say significant. Look at my value, you see. F naught, 24.76. Let's check this one, 3 critical value, okay, related to this one. 312.21. Sorry, here. 5.953. Okay, good. Okay. 5.953. Okay, perfect. Okay, 953. See, it's in the rejection region. This is the rejection region. See, so you reject H naught. See, you reject H naught. That's why here that it depends on that. That's why that block design has to be taken into account, because if you do this one, you can see even that you're not going to reject that one. See, actually that we brought this up over here. We brought to the surface over here and discuss, or bring to the table and discuss for reason. Because if you design that one in this way, most of the time we have a huge variability among these individuals. Okay, their reaction times to certain drugs would be differ from the, because of their different the aspects of the human body or something like that. Those things to be suppressed by designing this one by the block design. See, when you do the block design, we get the better results. See, better results. So these are the steps you have to do by hand. When you do by hand for the question number 2, which is the first question from the homework 2, you just you don't have to write all this like that, but just simply put this one and build up these pieces. Go to this one, block 1, build up, and get the residual one, sum of squared error, write the degrees of freedom, write the mean squared error or mean squared residual, doesn't matter. Mean squared between, or you can say the model, doesn't matter. Okay. So then degrees of freedom important, then come to the conclusion. Okay. Then let's go to this one. This is the one that this one I don't think that to do a multivariate repeated mesh analysis by hand. See, by hand with the following that one part 3 to support to part 3 for that question number 2, which is the first question from the homework 2. We go to now multivariate analysis, which is given by this output. I'm sorry, this one. This one. See, these ones. We are trying to talk about these ones. Okay, some of these. Okay. Okay, let's see that how it's gonna work. Look at how to build up the multivariate. Instead of looking at this one univariately, but individually, you can put the pieces, all the pieces together. See, this is same thing that we have seen. Or at least this one. Or equivalently, you can write this way. Mu1 minus mu2 equal to 0. And you can separate this one as like a 3 separate conjectures, 3 separate propositions, 3 separate hypothesis. See, mu1 minus mu2, 2 minus 3, 0, mu3 minus. To support this one, you have to separate, you have to get these combination as well in the data, because we're not gonna look at, now we're gonna look at these 3 at the same time. Instead of looking at this one the way that we did in univariate case, we're trying to split this one this way. You have a 3 hypotheses being tackled at the same time. This one, and this one being tackled at the same time. To support that one, you have to adjust your data, y1 minus y2. See, you had a y1, y2, y3, y4. Now you're going to say y1 minus y2. See, that differences now come like this. See, y1 minus y. See, you can see clearly that when you see 1, see, 30 minus 28, like that. See? So do we draw all the data. See, then you get that one. See, then you're gonna do the y2 minus y3 minus. Then they're gonna find the mean for that guy, mean for this guy, mean for this one, and their variances or their standard deviations. And put it up. See, that's the row vector of mean differences here. Mean differences. Okay, I'm talking about. I'm gonna tackle all at the same time. I'm gonna get this one, and this one together as a vector. See, that's called the row vector of mean differences. See, that's the mean differences vector. See? So that's the mean for the differences. That's what mean, not the difference between the mean. That means the mean of the differences, okay, of the data. See, I denoted that one by, see, I call that one differences D. In order this one y bar to average, and I put this an arrow to indicate it's a vector, and I put transpose. Normally it comes like a column vector. It's being given as a transpose. Normally row vector, normally that it should be the column. See, if it is in row as a row vector, that's a transpose. So this is a vector. I'm going to tackle all these at the same time. Now you might be thinking why we didn't do that one over here. We don't have to. That's why we call that one univariate. And we try that one univariate way. And then now the same thing. Now, instead of doing that one, now we're going to go ahead to answer your question. Then we're going to go ahead and get it done in this one, multivariate setting. Everything tackle at the same time. See? Then we know that under H naught, when H naught is true, under H naught means that this one true, you are that if you go to this difference, okay, mu1 minus mu2, let's say mu1 minus mu2 for my convenience. Okay, one, I'm gonna narrow down to only one difference, okay? Same setting will be applied to all these 3, but I'm gonna say y1 minus y2. Related to that one, your hypothesis would be mu1 minus mu2 equals 0. If you assume this one is true, under that one, your difference in mean, see, D bar stand for the difference in mean, sample mean, okay, sample mean. See, this should be actually come like this way, okay. This is what I'm talking about. See, y, get the reading difference and their mean. Okay, difference and mean minus the mean difference, which is 0 taken out, divided by their standard deviation, divided by how many that one being, see, this is what is distributed, is distributed. This tilde means is distributed. Distributed according to what? Distributed or follow T distribution with the degrees of freedom n minus 1. N minus 1, see, T distribution. Okay. Your difference in mean. That means whatever you get, this one, see. The mean of the difference. The mean of the difference of this guy, 0.8. But I'm not going to plug in 0.8. What I say that if you repeatedly do this one, that will be fitting into a distribution. You know that for your own this data set, you can calculate this one. There's nothing wrong with that. But it won't distribute it according to this one. If you plug in this D bar, which is 0.8, okay, here, and divide by square root of this one, divided by square root of 1, 2, 3, 4, 5, that would give you a specific value. It won't fit into this distribution, but it is one of the values coming from this distribution. We're going to assume this is also going to change from the different the data set. Instead of this one, someone else might have done this one, or you might going to do this one again, and you're not going to come up with the same result. It's going to vary. That variation is they call the sampling distribution. Can you remember we had that broader discussion in previous class? So because of that, you can say that whole number of t values, you can say I can calculate d values. So many d values for repeatedly you do this one through the Monte Carlo simulation. You can do this one like 1,000,000 times, 100 times, 1,000 times, 100,000 times, or million, trillion times. Those are you're going to arrange ascending or descending order and then get their distribution histogram. You can draw the histogram for that one. For that histogram, you go to the average. For that average, you can same as like a average would be the same to get it from that by substituting those values. Okay, that's kind of a broader discussion we had. That's why we have standard deviation for that value, not for one. The standard deviation has been given for that variation in these differences. These are for the different distribution. If you draw that different histogram, you can draw the histogram for the D bar. Sorry, okay, like that. Okay. For D bar, see D bar here. So then for the D bar, you can go to the center. Center would be what? Center would be nothing but the difference in this one. That's a center. Again. And do we have variation? Yes, there's a variation. That's variation in this one. But do you know that one? No. But do you know that one related to our data? Yes. That one you can plug it. But anyhow, that's how we built in up this one. Then I'm gonna square. When you square, it's gonna be like this. I'm gonna split this one. Look at what I'm doing. I'm gonna put the D bar here, and then put this into the middle and take to the numerator. Still, I'm working with the numerator case. See? That's the same thing. If you want to tackle all these, I'm gonna put all these together. See? N is N. This is D bar is replaced by what? Means. All means I'm going to take into account. Rather than earlier I took into account only 0.8. I say no. Give me the vector. Give me the mean vector. Mean vector of the differences being given its transpose. And in the middle I have what? Standard deviation. Instead of standard deviation, in this case you have what? Variance covariance matrix. The matrix. It's the same guy come back again. See? So I tackle 3 means instead of 1 mean. I put 3 means they are transposed. Instead of 1 variance, I'm going to take into account all the variance, not this one only, not this one, these three only. I need that covariances between these ones too, and this one too, this one too, those covariance. That's why I have a variance covariance matrix. How do you calculate? Between what and what? This variable, this is the variable. I'm talking about this variable, y1 minus y2, this variable and this variable. If you want, you can call with a new name for this one. D1 or something. Anyhow, D1, this one. If you want, so you can say D1. This is a D2, D3. Okay, for my convention, I'm gonna say if how do you calculate the covariance between these two? See, you go to the reading 2 minus its mean. See, go to the next one 12 minus its mean plus keep going for all the entries minus 4 minus its mean plus this one plus and then 4 minus this guy times this guy minus this one. Keep going until you're done with all the readings and divide by n minus 1. N is 5 and then you get this answer. And the same way you did this one with the y1 minus y2 is that variable, this variable with that variable. So you're going to say 2 minus 0.8 times minus 8 minus 16.4. See, that's a plus now. You do the same thing for that one and divide by n minus 1. Then you get this one. Then you do the same thing between y2 minus y3 and the other two variables. Then you get this one to build up that your variance covariance matrix. These are the covariances. This is y1 minus y2, that variable. This is a y2 minus y3 variable. This one y3 minus y4 variable. Okay. So these are, we already know 13.2 from the very beginning. See, those are going to be in the diagonal. They are in the diagonal. The rest would be, displays. You need on the one side. Upper triangular matrix or the lower triangular matrix doesn't matter because they will be repeated on the other side. Negative 8.6 here, negative 0.3, I calculate, and negative 90. See, and then you can get the inverse. See, you get the inverse. Okay, get the inverse. See, that's the inverse. Then plug in into this one. See, I think I'm cutting out something over here. Okay. 5 vector, this one, see, vector. See, this one is what? What's the size of this one? This one we're going to say 1 by 3. 1 by 3, that's the size, that's the dimension. This one 3 by 3. This one what? How many rows? 3 rows. 1 column. Okay. Here, 1 row, 3 columns. 1, 2, 3. So when we multiply, they get cancelled out. This cancel out, this cancel out, this cancel out, this cancel out 1 by 1. That's why you get a number. Okay. You can do by hand. Okay. When you need the inverse, you can get the inverse by just using the SAS.
Professor, how are those inverses calculated? Like how did we get 0.458? What did we invert?
You invert this guy to look for how to invert the matrix. See, this inverse. This is this guy. Okay.
The entire matrix.
The entire matrix. Exactly. Let's say, for instance, that I can show you something like that. Let's say that you have a 2 by 2. Okay, rather than going to this one by hand. If you want to do like, let's say that you have a no, it's gonna be a little bit expensive, but you put this one onto the SAS, it's easy, I think. Okay, put to SAS or RO that calculator, they give you that inverse right away. Okay, if you get stuck, we can talk about that one tomorrow again. Okay, so see, then put this one, and we go further up over there too. That t square not enough. t squared being multiplied by this factor will give you F distribution. You had a T distribution. See, in the beginning you had a T distribution very similar to what? T distribution very similar to this one. See, it's T. It's T distribution. Symmetric. But once you square, the interesting thing becomes skewed. See, only one sided starting from 0. This is not like that. It's going to go from negative infinity to positive infinity. See? Having 0 in the middle. But once you square this one, see, t squared, and multiply by a certain factor, it becomes a F distribution. See, so the degrees of freedom are related to G minus 1, N minus G. G means number of groups, N means number of entries, okay, number of individual participants. With this one, you get the degrees of freedom. You calculate this one. I'm going to call this one numerator degree of freedom, which is that one, is the denominator. Okay? So whatever the value you got from here, okay, you set this up, okay? It's easy. Or in that even Excel, you can calculate, get this stuff to one shot, okay? So then F value, then you're going to check again as we did see. You go to the critical value. Critical value is this one. Okay. And 2, 3, sorry. 2 and 3. Sorry. Did I put right? Should be numerator 3 and 2. Sorry. Over here. I have to double check that one. Anyhow, that numerator one comes from the top. I'm going to double check that one. Numerator one. Numerator, we have what? Degrees of freedom, N minus 1, G minus 1. This factor, because of this factor, you divided by that. Make sure that degrees of freedom will properly set up over there. So 3 and 2. Okay, G minus 1. Okay, right. But here, not right. This should be 3, 2. 3, 2 for the 0.05. If you use the 0.05 or 0.0, depends on what. 0.05 is the numerator. Is the denominator. Okay, then let's put 0.05, 3 and 2. Let's try this one. What? If here, okay, here. Oh no, the top one. I'm sorry. 0.05, 3 and 2. No. Oh no, this one T. I'm gonna go to the P. If critical value probability 0.05. 05, 3 and 2. 19.16. No? 19.16. 19.16. Okay.
Oh, he's on his way.
This one is 20.443. See? And then it's going to be in rejection region. You rejected. It's very consistent with what we got from the univariate case. Okay. In the multivariate, that in addition to that, this is a multivariate setting I'm showing over here, but I can come to that real quick. Something that some you see some Wilks lambda, and then those some, but you don't have to worry about these symbols. Okay, that's how it is. Okay, but I'm giving a rough idea what's going on this printout. Okay, this one. Okay, so those are go here real quick and then I have the other okay, I'm gonna go to this one. Oh, sorry, we have resuscitate. I'm talking about this one. Okay, here, see, Wilkes lambda, Pillai's trace, Hartlin Lawley, that trace, rho is greatest root. How they are coming from? They are coming from when you talk about them, they come in this kind of setup. That, as I said earlier, I'm gonna say I goes from 1 to G, number of treatment groups. J goes from 1 to Ni. Ni means if they have the same number, you put N. If you have a different numbers, Ni, because based on that, how many treatment go to that particular treatment group will give you subjects in each treatment group. And K means number of dependent variables in response of each treatment group. See? Now, how many dependent variables in that particular treatment groups? Some of that term. See, P, how many variables? See here, look at how many variables. P here in this case, 3. P equals 3 variables. 1, 2, 3. That's then my K gonna go from 1 to P in multivariate setting. Okay, MANOVA, I'm trying to go through the MANOVA and then build up that what's going on for that one. Under the MANOVA, the multivariate analysis of variance, in which that we're going to take into account that the several variable, response variable, we tackle at the same time, same way we did here. See, look at 3 response variables I'm tackling at the same time. See, with the aid of matrix analysis. That's what we call the multivariate. See, not univariate. Univariate means only one at a time. I'm tackling 3 of them at the same time. That's why I'm using matrices and then the vectors. That they are the same discussion that I'm going to extend in order to build up those statistics. So that's why, as I said earlier, I don't use K for G here. I use K here as an index. If index is going to go from number of variables 1 to P. How many observation? 1 to N. In our example, previous example, drug example, I have a N equals 5. G is how much? 4. P is how much? 3. Because in the beginning we had like this, but later on we converted to the multivariate setting. See, univariate setting we did that one too. In multivariate setting we're gonna do 3 of them at the tackle at the same time by taking the differences. Because we have to do like this way because we had this situation. I wrote the same hypothesis in this format equivalently. So if you once you write this one, it seems like you have a 3 conjectures to be tackled at the same time, take into account. If it's the case, you have to adjust, transform your data accordingly to fit into this one. Once you do that one, you have a 3 variables, new 3 variables. Those 3 variables you tackle at the same time. That's something I'm talking about here, the same discussion. Okay. So see, the population 1, those are, you can see, Y1, 1, 1, 2, 1, and 1, 2, 1, 2, 2, 2, 2, and like that. Okay, so it's a G1, 4th one, you can say 4, 1, 4, 2, 4, 5, like that. You don't have to worry about this assumption too much. Okay, maybe then the data come like this way. See, you have the data for each thing. Okay, see, like that. See, this on rows, columns, and inside the matrix. K stand for how many the variables. All population has a common matrix sigma. Each population is multivariate normal. That if you go and then look at the averages too. Okay. See, is the data going to be like this? See, 1, 1, 1, 1, 1, 2. See, all the for the everybody for the first reading. See, like that. This is first person. See? First person. See, first group. I'm sorry, first group. See, look at that how they've been given. First group, individual, how many variables? Okay, look at this. This one, see, it's clear here. See, first group, see, second individual, it has its information. It's his information. Okay? Let's say that all the information, see how many variables for that person, see, but it's in the first group. First group, second individual. If variable, see. First one, 1, 2, 1, see. First group. Second individual. And for period, so this one, see. First one. So you have see, something here, see. The variable go from see, here, here, here. 1, 1, 2. So 1, 2, 1. First group, first group, first group. Second individual, sorry. First group, second individual. First group, second individual. Like that. See, in this case, see, we have that readings, okay? So you can relate it, but don't worry about that one too much. But I'm trying to say that how, okay, see, like this example, let's see, if I show this one. These are just the readings. See. I goes from, see, G equals 3 groups. Okay, 3 groups. 1, 2, 3. And see, N1, this one, this group has how many entries? This group has 3 entries. 1, 2, 3. This group has 2 entries, 2 individuals. This one involving 3 participants, 2 participants, 3 participants. That's what I mean. And how many information we're going to extract from each individual? 2 information. Let's say that GPA and age at the same time, something like that. That's the multivariate case. So this is the group. This is the group. The way that I set up, this is the group. Okay, this is the group. This is the number. See, 1 group, second group, third group. First group has 3 entries. Second group has 2 entries. Each entry has 2 variables being tackled at the same time. So they are, see, within sum of squares came like this one. You don't have to worry about this formula. I'm getting a rough idea. Between come like this. Okay. They are degrees of freedom. Total number of groups minus the number of groups. See? Total sum of squares. And Wills lambda is nothing but, see, this W, this one, see, within divide by B plus W, which is total. See, Wills lambda. See, that's the one you're going to see from the printout. They have done this one inside. Whoever developed this one, that there are SAS developers that who are really good in the data, the statistics and the data analytics, machine learning and everything. They know they developed this one. See? So you see this one. The distribution of Wills lambda have a different distribution based on that what you have. See, these are that P equals 1. If you have 1 group to be more than 2 groups, it's gonna be distributed. Not only that guy, 1 minus lambda over lambda, whole thing distribute according to this one, F distribution. Okay. If it is P equals 2 greater than this one, according to this one, look at the degrees of freedom. It's gonna vary. P means number of variables they taken into account. Okay. How many groups like that? Okay. How many groups? Number of variables. 2 groups, like that in multivariate case. Okay. And the Bartlett shown that this one, at the end of the day, instead of going with the F distribution, they can go to the chi-square like this one to tackle the chi-square too. That's how you see that F with the lambda. Okay, F with the Wills lambda. See, Wills lambda F. denominator degrees of freedom, see, based on this setting, based on these properties. What kind of a distribution, see, it's going to fit into, by looking at, you have to look at that one and see how many p variables they're talking about, how many groups they're talking about. Based on that one, either this F or this F or this F or that F. And on the other hand, and when you're going to compare, see, all the averages, then that can be fitting into chi-square too. Okay? Like that. Okay, but that's a rough idea. At Hartlin Lawley, that trace would be the trace of that BW inverse one that we don't calculate. They do that one. B and W. See, B means between, W inverse. That one trace. Trace means diagonal elements. They're gonna add together in that one, and they have squared that one. See, Pillai. Pillai is that instead of that one, he made some kind of a modification to this one. He got not the product. Okay, he got the B plus W and got the inverse and multiplied by B. Pillai and Bartlett. Roy's largest one is the largest eigenvalue of this guy. You might be thinking, what is the largest eigenvalue? It's nothing but BW inverse that matrix eigenvalue. The largest one called the Roy's largest root. Pillai one is what? This one. How do you get the B and W? You see, B and W is this one. We have a formula. We can tackle all of these at the same time. Okay? That's how they get that one. Roughly, okay. And see, and the Roy's largest is also sometimes used in this format. WP is the largest eigenvalue divided by 1 plus lambda T of this one, you know, largest one coming from the W minus 1. That matrix eigenvalue, can you find? Yes. We don't do it by hand, but by computer will do that. And even for the by hand, we know how to do it as of now. See, sometimes they can show like that. On the other hand, see, the second one, the lambda, see, Wilks lambda is nothing but 1 over square root like this one, or this one. Get the see eigenvalues of the lambda. See this one. See? If you have a p-variate, you have p eigenvalues. See? They should be add k equals 1 to p. See? Or t naught like this way, or v like this way. See, so many things. The same thing. See, t naught means Hartlin Lawley. Sometimes they express in this format. We put the Pillai Bartlett. See, sometimes they express this way with the aid of the eigenvalues. Whose eigenvalue? This guy's eigenvalue. See, so many ways. But Wilks lambda test. Then we have a test. Okay, the test is done this way. That if the null hypothesis is true, then your degrees of freedom like that. That's for the test. There are two tests. Wilks lambda test to test that you have what? This guy. This one. See, multivariate analysis of variance is done by Wilks lambda. Sorry, this test. Yeah, Wilks lambda test. See, let A like this, B like this, If the null hypothesis is true, it's like this, but we don't do anything. Okay, these are very heavy. These are multivariate, extremely heavy. But normally that like a very rigorously that some top universities, they very rigorously they learn this one everything by hand, plus that by using that computational tools both. That's why they become like a so that very excellent the program developers at the end of the day. It's important. So do we have like that if you want to have like a kind of like a, but this is see. These are the main assumptions that we're going to talk about: the independence of the observation. In that, I'm talking about repeated mesh analysis, the multivariate, the sphericity, and then the circularity. This is the one we tackle that one mainly. So we talk about that one tomorrow. Okay, I'm going to go ahead and stop over here because I have to get into the other class. So we mainly talk about that one, and we're going to finish that homework too at the same time. Okay, we can discuss that one too. If you get stuck something, then we can talk about. Okay. So see, this one, see, mainly that we have a 2 epsilon. Epsilon is that measurement of the sphericity. Sphericity means like a, that's the variances are different. See, basically sphericity refers to the equality of the variances of the differences between levels of the repeated measures. How far that one different is measured by 2 ways, see, mainly. So once you do that one, see, once you get that one, when you convert to that y1 minus y2, y2 minus y3, y3 minus y4, you're not going to have a covariances. You had that one earlier, but once you have that one, see, the extent to which the covariance matrix derived from the sphericity is reflected in the parameter called epsilon. That epsilon being given by this formula, by this thing, see, greenhouse and guys, this one, and see, another alternative formula we have, and the Huynh and then Feld epsilon. See, like this. Okay, we can see, and there are 2 tests for that one too, and then see, and so that I don't think it's going to be a big deal. We can just simply that add this one to our homework and then move forward tomorrow. See, this formula, some cases that formula being given, you have to plug in into the formula. Okay, we can continue the same discussion tomorrow. Okay, so do you guys have any questions? If not, I'm gonna go ahead and then take off, and then you guys have a good night. See you tomorrow, and then stay safe and be well. Okay, take care. Okay,
See you
bye bye.
tomorrow.
Okay, see you then. Take care. Thank you very much. Thank you.
Thank you. Bye.
Thank you. Bye. Thank you. Bye. Take care.